We'll look into the impulse reaction turbine of 50% type or off degree type. That is Parson's turbine. Impulse reaction turbine with similar blade sections. Okay, and R is equal to 0.5, that is half degree turbine, that is Parson's turbine. If you look into this turbine, there are certain things which we need to look at. That is, see, the most important thing is the specific volume. The specific volume of the steam increases with the decrease in pressure due to expansion. Whenever the pressure drops, means that's expanding. So corresponding to that, actually, I could see that the specific volume is going to increase. Here's one thing. And then the second point, we have what is called as heat drop per stage. The heat drop per stage. Stage means it includes the stator and the rotor. Per stage compared to its preceding stage. Okay, heat drop per stage when compared to its, we call it as a preceding stage, increases. Preceding or previous stage increases. Okay, and the specific speed ratio, the third point, the specific, or we call it as a blade speed ratio. We call it equal to the other, call it specific speed. Let me call it as the blade speed ratio will also vary. So blade speed ratio will also vary from one row to other row, from one row of blades to other. Okay. What is this actually? Because of all those things, my degree of reaction will vary. See, because of all these three, my degree of reaction will vary. It's difficult to keep it 0.5, it will be 0.6 or 0.7. Sometimes it will be around 0.8, 0.9. So this kind of situation we used to get in most of the impulse reaction turbines. So to mitigate for this actually, what Parson, being an engineer, I think what he did was actually, is it possible by making my inlet velocity triangle and exit velocity triangle the same? If I'm able to do that, then my R can be kept at 0.5. That is a level. Okay. To do that, so if I try to put a velocity triangle for that, this is my U, and I have my V1 and VR1. Okay, this is my VR1, and this is your alpha 1, this is your beta 1, VF1 and VW1. Okay. Now, what I did, suppose if I try to draw a line exactly at the center, say exactly at the midpoint, right? Exactly at this midpoint, if I have and try to get a mirror of it. If I try to get exactly a mirror of it, so this is my, if I call this as A, B, C, D. So if I am able to get a mirror exactly of this particular mirror to the right side of it, that is my exit velocity triangle is just a mirror of it. So if I want to do that, I have to get this is my V2. Okay, sorry, this is my VR2. So that's my VR2. So dimensionally, this VR2 or should be equal to V1. If that is the case, then what will happen to your beta 2? So this particular angle, beta 2 should be equal to alpha 1. If I am able to ensure that if beta 2 is equal to alpha 1, then my beta 2 or your whatever you have, no, that particular thing, your alpha 2, what are we called? So if I try to close my triangle like this, so this is my V2, VF2 and VW2, my alpha 2 automatically becomes alpha 2 will be equal to your beta 1. So under this condition, what will happen? A, B, C, D, we call this as E, F. So at any given point, if I take ADB is one triangle, will be equal to ADE. So at any given point, if I have a triangle ADE is equal to triangle ADB. So if I'm able to satisfy all these conditions will lead to a similar velocity triangle. And what we have seen in case of a reaction cases, impulse reaction cases, this VR2 will be increasing. So VR2 will be increasing, which will be more than your VR1, which will be more than your VR1. That's the reaction case. To mitigate for all those things, so Parson came up with this one design. So it has to put it on the turbine stage. What I did actually, if this is my casing of my turbine, so this is my insulation, a heat loss. So what it has to be, the whole turbine should be of diverging. Okay, if I'm able to have the diverging section steam turbines and which are of equal blade sections. If it is of equal blade sections and equal angles, if I'm able to do this, I'll be able to get the required equal velocity triangles or equal energy levels, which will lead to a degree of reaction or the conversion of the energy. So I have 50% your whatever I have in the rotor, no, that won't be kinetic energy, it will be only pressure energy. And we have other 50% impulse, 50% reaction. So I'll be able to exactly able to maintain the 50% reaction if I'm able to do this. So if I have a set of rotors, so this is my stator like this. I have a shaft. Let me have a shaft. I have a shaft like this. This is my shaft. So I have a set of rotors. See this, the rotors will be something like this. So I have a set of rotors, which will be just like your turbine. This will be expanding turbine, and I do have this is my stator, this is the stator, this is S is a stator, R is a rotor, S is a stator, R is a rotor. Okay, and if you look at the cross section of it, then given point, this is my stator, and this is my rotor. This is my stator and rotor. The blades will be like this. The blades will be like this. They are all aerofoil file shape, and it will be going like this. Your stator as well as your rotor will be of similar cross section. Okay, so let me write that. So, what did Parsons proposed actually? He proposed that the moving blades. He proposed that the moving blades and the fixed blades, the moving blades and the fixed blades cross section, or the blade cross section, fixed blades are the same and with blade cross with the same or are having the same blade cross sections, or having the same blade sections, we can call it as. So these conditions were met in your corresponding, in your what we call it as Parson's turbine. So what will happen if my beta 2 is equal to alpha 1, alpha 2 is equal to beta 1? What I'm going to get actually here, so I'll be having my VR2 is equal to V1 and your V2 is equal to VR1. These two conditions will lead to what we call as a simple reaction turbine. That's a Parson's reaction turbine with R is equal to 0.5 with equal velocity triangles on either side. Okay. Now let us look. Already we have seen. So let us look at the what we have, what we call it as the gross stage efficiency or the optimum value of your speed ratio. Expression for the gross stage efficiency and optimal of rotor and your my fixed blade and the rotor. Okay. The isentropic heat drop, isentropic heat drop in a stage. What is the stage actually? The stage is nothing but it's a pair of stator and rotor. Okay. What does it contain? It consists of your enthalpy drop for the nozzle or the stator plus enthalpy drop for the rotor. Okay, enthalpy drop for the stator and enthalpy drop for the rotor. Now, let us write for the, so if I call this as expression number 1. Okay. What is the enthalpy drop for the rotor? The enthalpy drop for the rotor is given by, if you call this as V1 square minus, you have a psi, what is called as your carryover coefficient. So psi is my carryover coefficient is equal to psi into your VR1 square. See why I have taken VR1 square? This is with respect to relative, because I am taking with respect to it enters at that particular velocity V1 and it goes out of with a relative velocity with 2 times your corresponding what we call it as your nozzle efficiency. This already we have discussed. So this will be the expression for your rotor. Now if I take the velocity triangle and use the cosine rule, so from the inlet velocity triangle applying the cosine rule. So what is my VR1 square? Go and see. Consider triangle ADB. So VR1 square is equal to V1 square plus U square minus 2U into V1. Okay, into cos alpha 1. Okay, let me write that. VR1 square is equal to V1 square plus U square minus 2U into V1 into cos alpha 1. Okay, and already we have defined phi is equal to U by V1. So I can substitute for U in terms of V1, or U is equal to phi into V1. Just already whatever we have written, we are rewriting. So therefore, my VR1 square is equal to V1 square plus phi square into V1 square minus 2 into phi into V1 into V1 into cos alpha 1, or I can write my V1 square outside. I can write it as 1 plus phi square minus 2 phi into cos alpha 1. Let me call this as expression 2. Okay. Now let us, if I substitute for this VR1 in this equation, let me call this as 2, let me call this as 3. So if I substitute for VR1 square in 2, substitute for VR1 square in equation 2, what I'm going to get actually, I'm going to get delta H for the rotor is equal to your V1 square as it is minus psi into V1 square into 1 plus phi square minus 2 phi cos alpha 1 whole thing divided by 2 times your nozzle efficiency. So what I can do, V1 square I can take it out. So if I take my V1 square outside, so delta H of the rotor is equal to V1 square divided by 2 times nozzle efficiency into 1 plus phi square minus 2 phi into cos alpha 1. So let me call this as expression number 4. Okay. Now what will happen if I have a fixed, see, you have a fixed set of blades. Okay, each row of fixed blades. See, except for the first, see, first stage we have a nozzle. And let me write that. Except for the first stage, except for the first set of fixed blades. First set of fixed blades, the subsequent blades will have a gain in kinetic energy, or will see will be similar. The subsequent fixed blades, I'm speaking of only fixed blades, will have a similar gain in kinetic energy. Okay, what it will be actually, if suppose I have, see, it's something like V1 square minus your psi into V2 square by 2, okay, which will be equal to V1 square. So this is something like fixed going out, psi into VR the next one. So it will be with respect to the rotor, what it's going to see. So this should be same. One will be with respect to the stator, what is going out, and one will be with respect to the rotor. Okay. Now, the isentropic heat drop for the rotor and the stator should be the same in that case. So, whether for R is equal to 0.5, whether this expression are the same. So, what I can conclude, therefore, delta H for the nozzle also, it will be same as your rotor, that is V1 square minus psi into VR1 square by 2 times your nozzle efficiency, because my delta H of nozzle is equal to delta H of rotor. So this condition is only for R is equal to 0.5, because let me write that also. This is hence R is equal to 0. Only for 0.5 condition this is prevails. Now if I write this expression, what I'm going to write? I'm going to write that expression. That is, if I add this plus that, what it will be? If I substitute for this in expression number 1, so what it will be? So I'll be taking equation 4 and add it. So therefore, equation 1 becomes what it is actually, delta H of, that is isentropic. Everything is isentropic. That is nozzle plus delta H of rotor is equal to V1 square by 2, that is nozzle, into 1 plus 5 square. 1 plus, what is it? Yeah, 1 plus 5 square we have this psi is also there. Okay, we have this psi. Missed out. Expression has to write it also. V1 square, if I take it out, this will be 1 minus psi into 1 plus 5 square minus 2 pi cos of. Yeah, let me stop it. So for each and everything I have to write it. This will be 1 minus psi into 1 plus 5 square minus 2 pi cos alpha 1. The same thing write again. Okay, plus V1 square by 2 into efficiency of nozzle 1 minus psi into 1 plus 5 square minus 2 into 5 into cos alpha 1. So off plus off, it is 1. I can write it as V1 square by your nozzle efficiency into 1 minus psi into 1 plus 5 square minus 2 pi into cos alpha 1. So this will be the expression for the enthalpy drop in both per stage. Okay, this is the isentropic enthalpy drop per stage. If I call this as expression number 5, let me call this as expression number 5. Now, what is gross stage efficiency? It is work done by isentropic heat drop. So before that, let us define what is work done. So we know that work done, okay, work done per kg. That is, usually we go with specific work. Work done per kg of steam is given by your VW. Okay, what is your VW? Once again, already we have defined, that is your VW1 minus VW2. Already we have defined that. Okay, we can write that as VW1 minus of minus, that is plus. So I can write that as VW1 plus VW2 into U. So let me call that as equation 6. Or we can simplify that also. We can simplify that. What is my VW1? VW1 I can write it as, for the velocity triangle, I can write it as V1 cos alpha 1. What is my VW2? I can write it as, I can write in terms of, already we have seen in terms of cos beta 2. Okay. So just go here, use your cosine. So I go to velocity triangle here. So go to my velocity triangle. So I have my beta 2. So I can write, say I want VW2. So cos is my cos beta 2. If I do here, what is my cos beta 2 is equal to VW2 plus U, okay, divided by your VR2. Okay, U plus B. So now, but what is my VR2? VR2 is equal to V1. For this condition, it is V1. Then what will be your VW1? So V1 cos beta 1 minus. So VW2 will be equal to V1 cos beta 2 minus U. I can write in that particular fashion. So what I will write for the cos beta 2, I can write it as minus U into U plus VR2 cos beta 2 into U. But VR2 is equal to V1. So as my V1 is equal to VR2, the same expression I can write it as V1 cos alpha 1, okay, minus U plus V1 cos beta 2 into U. What is your beta 2? I can write that also. So not only that, your beta 2 is equal to alpha 1. I can write that also. I can write beta 2 as alpha 1. Okay. Plus alpha 1, you have this particular thing. I can, so this will be V1 cos alpha 1. Okay. U into see V1 cos alpha 1 minus U plus V1 cos alpha 1 into U, or plus cos alpha 1. So you have 2 cos alpha 1. I can write it as 2 V1 cos alpha 1 minus U into U. Okay, this is your per kg of steel. Now what is your phi? Phi is equal to U by V1, or I can write U is equal to phi into V1. I can write my W is equal to 2 into V1 into U. So that is phi into V1 cos alpha 1 minus, I can write phi square into V1 square, or I can take my V1 square outside. This will be V1 square into 2 phi cos alpha 1 minus phi square. Let me call that as expression number 6. So I have two expressions. One is for your enthalpy isentropic heat drop per stage, then have the work done. Okay. Now what is the gross stage efficiency? Therefore, the gross stage efficiency, the gross stage efficiency is given by, is equal to the work done per kg of steam divided by, okay, the isentropic heat drop or enthalpy drop. The isentropic heat drop per stage per kg. Okay. Now let's substitute for this. What is the work done actually? It is V1 square into 2 phi cos alpha 1 minus phi square. whole thing divided by V1 square by the nozzle efficiency into 1 minus psi into 1 plus phi square minus 2 phi cos alpha 1. Okay. Is it possible to further simplify it? So take the nozzle efficiency to the numerator and V1 square, just they cancel out. So this will be the cross stage efficiency equal to nozzle efficiency into 2 times your phi into cos alpha 1 minus phi square divided by 1 minus psi into 1 plus phi square minus 2 phi cos alpha 1. Okay, this is your gross stage efficiency. So if you want, I can simplify further. Okay, so I can put it in some other form. I can retain the nozzle efficiency at the top and bring this 2 phi cos alpha minus phi square to the bottom. So I can bring it and I can simplify it. So then some of the things will just simplify and I'll be getting some other form, or you can retain as it is. Further simplify, if I do that, it will be something like this, equal to your nozzle efficiency one minus psi into 1 plus phi square minus 2 phi cos alpha 1 divided by 2 phi cos alpha 1 minus phi square, or I can take it out, is equal to the nozzle efficiency as it is, right? 1 minus psi as it is, so 2 phi okay, I can open the bracket and see. If I open the bracket, this will be 1 minus 1 minus psi, so minus phi square plus 2 phi cos alpha 1 divided by 2 phi cos alpha 1 minus phi square. Okay. So if I take for each and everything, if I take 2 phi cos alpha 1, so I'm left with, so further simplification, if you want, you can do it, or you can retain as it is. I think you retain as it is, that's better. Rather further simplification, so it's difficult. Okay, you can retain as it is. So this is your equation number 7. This is your equation number 7. Now I can maximize this actually. If you look at it, now for a given alpha, see, for a given alpha 1, that means it becomes constant. I can maximize the gross stage efficiency by differentiating with respect to phi and equate it to 0. Okay, if I equate it to 0, if I do that, so that's the only option for me. If differentiate your equation 7 with respect to phi, because phi becomes a variable. Phi becomes a variable. So for maximum efficiency. So what will happen if that is the case? I am left with only this particular part. Differentiation will be only this particular part. So if I equate it to 0, I am left with only 2. If I differentiate that, because rest all will just simply cancel out. I'll be getting 2 cos alpha 1 minus phi square differentiation is 2 phi. Okay, and your cos alpha, your phi will be equal to, or phi max, or we convert the phi optimal is equal to cos alpha 1. Okay. For that case, if I substitute cos alpha 1, phi is equal to cos alpha 1, if I substitute there, my gross stage, so by substituting after phi optimum is cos alpha 1, I'll be getting my gross stage efficiency maximum. I'm going to get, this will be my expression, you can try this out, will be cos square alpha 1 divided by 1 minus psi into 1 minus cos square alpha 1. Please try this after substitution or getting the same expression. What I want is, see, this particular expression is there, no? This particular expression, one is the variable is phi for a given alpha 1. So, alpha 1 is the your flow angle at the inlet. Okay. So, we can verify how this particular thing will vary. How this particular, see, if I have a multi-stage single row impulse turbine or a multi-stage uh, impulse reaction turbine, how the phi value will have an impact on your gross stage efficiency. So we have seen two expressions. Okay, we have two expressions. What the people can do is actually take this expression and use an Excel. See, use Excel or code. If you want, you can write the code also. Use Excel or a code. So try to plot this graph. Try to plot this graph and verify this. So on x-axis, I can have phi, which is u by v1. Okay, I have u by v1. On y-axis, you take the gross stage efficiency equation. Gross stage efficiency equation. You can verify both expressions. See, what are the expressions? One is the multi-stage single row impulse turbine, which we studied in the previous unit. If you take that and try to verify it, if you try to, this is the nature of plot, you may superimpose one over the other. If I look into that particular thing, so it is 0, it starts with 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, let it be in steps of 0.1. Okay, let me steps of 0.2. If you start with 40, 50 on the y-axis, efficiency, let it be around 50, 40 or 60, 40, 50, 60, 70, 80, 90, 100. If you have this efficiency, so you may get a plot something like this. For an impulse machine, you may get something like this. And for a impulse reaction multi-stage, you may get a plot of this nature. Okay, this is for multi-stage impulse reaction turbine. Okay, and this is for plot for a multi-stage impulse turbine, single row. So what is the advantage here? See, you can take alpha is equal to some number. So each people can try for maybe alpha is equal to 15 degrees, or one can try with alpha is equal to 20 degrees, and other one can try with alpha is equal to some 25 degrees, and you can take CB is equal to some 0.85 or 0.89. This you need this actually, and if you want, you can take some nozzle efficiency as around 0.9 or 0.95. You have to make some assumptions. And for all those things, R is equal to If I take for R is equal to 0.5, what will happen? You can verify it. For a multi-stage impulse reaction turbine, for R is equal to 0.5, one can try with alpha 1 is equal to 15, one can try with alpha 1 is equal to 20, another at 25, or in between number 15 and 80, 20, 18 degrees. Okay. Once you have all these things, you can try to superimpose. The nature of plot may be the same, but the numbers may vary. You can just verify those numbers. What is the impact of these numbers? You can verify. Okay. And you can check out. See, we got your phi optimum is equal to cos alpha 1. So, for example, if I take cos 10 or cos 20, so what will be the corresponding, what will be the value of your phi optimum? If I take 20 degrees, my phi value will be around 0.94 or 94%. If I take alpha is equal to 15, okay, I may get a number around 96 or 97%. So lower the angle. So if you keep, see the alpha, if it goes down, your phi value also will increase. Or if alpha is equal to 25, I may get around your phi optima will be around 90% or 90.1 or whatever, 91%. So my gross stage efficiency will decrease with an increase in alpha. So that relationship you can try to bring in when you try to work on your on Excel file and try to come up with these numbers. Otherwise, until unless these equations, whatever the derivation I have done, those derivations you will be in a position to understand when you work to use that expression for varying values of phi. See, you plot from phi is equal to 0 to 1, you can point 1, point 2, you can put it at on x-axis. You will be getting those values. And gross stage efficiency also will get it. You may get a numbers 80%, 82%, 90%. So you may get around 90% the maximum gross stage, not more than that. 100% is ruled out. But a similar kind of plot you may get it. So please look into that activity. Take it as an homework and seriously try to learn this. Okay. And the last expression what we have is the blade efficiency. The blade efficiency. It's also called as the vane efficiency or blade efficiency. It's also called as the vane efficiency. What is it actually? It is a ratio of work done per kg to energy input per second, or what is the energy supplied per second per kg, whatever it may be. What is your work done per input? Right now we have seen already, we got the expression, that is V1 in terms of V1 square into 2 phi cos alpha 1 minus phi square. Already we have this. So we have the work done. So work done is given by, we have this is equal to V1 square into 2 phi cos alpha 1 minus phi square. Already we have. What is the energy input actually? That is, let me call it as energy input E in. This is actually your V1 square by 2. What is the energy input to the rotor blades? See, this is the energy input in the fixed blades. So this is the energy input in the fixed blades. What is the energy input in the rotor blades? It will be in terms of your relative velocities. That is your VR2 square minus VR1 square by 2. This is for rotating blades. So what will be the total input? What is the total energy input? So total E input is equal to your stator blades plus your rotor blades. VR2 square by VR2 square minus VR1 square by 2 for the rotor and V1 square by 2 for the stator. You just add it actually. This is the energy input for this is the total energy input. This is total energy input for a Parson turbine. Now, if I substitute for your what is my VR1 square, what is my VR2 square, all those things. Okay. Here, what is my VR2 square for a Parson's turbine? See, for a Parson's turbine, what will be my energy input? See, your V1 square I will retain as it is. What is my VR2? VR2 is equal to V1. I can write it as V1 square minus VR1 square by 2. This is because my VR2 is equal to V1. Okay. Now, what is my VR1 square? Already we have the expression. VR1 square, I can write it in terms of V1 square. Okay, VR1 square, already we have the expression. If you go back and see, VR1 square, we have this expression. Okay. Where is it? Yeah. VR1 square is equal to expression number 2. VR1 square is equal to V1 square into 1 plus phi square minus 2 phi into cos alpha. Okay, I can substitute for that also. So coming back, I can write for VR1 square like that. So total energy input E in is equal to V1 square by 2 less V1 square minus VR1 square, I can write it as V1 square, okay, it is equal to V1 square into 1 plus phi, 1 plus phi square minus 2 phi cos alpha 1 whole thing divided by 2. Okay, I can take V1 square by 2 plus V1 square by 2, I can write it as V1 square minus V1 square by 2 into 1 plus phi square minus 2 phi cos alpha 1. Okay, if I take 2 V1 square, if I take this also to the left hand side, I can write it as V1 square by 2. This V1 square, yeah. If I take 2 V1 square, this will be V1 square, yes. V1 square into, V1 square by 2 into 1 plus phi square minus 1 minus phi square. Minus into minus, no, it will become plus. Plus into minus, this will become minus. So this will be 1 minus phi square minus into minus, it is plus 2 phi cos alpha 1. Okay, this will be the expression for energy in for a Parson's turbine. Now, what will be the blade efficiency? What is the blade efficiency? The blade efficiency or the is equal to or vane efficiency is equal to, I will substitute for this. For the work done, if I substitute, it is V1 square into 2 phi cos alpha 1. So, it is V1 square into 2 phi cos alpha 1 minus phi square divided by V1 square by 2 into 1 minus phi square plus 2 phi cos alpha 1. Okay. For the simplification, I can take 2 outside, 2 to the numerator, and V1 square just simply cancel out. This will be 2 into 2 phi cos alpha 1 minus phi square divided by 1 minus phi square plus 2 phi cos alpha 1. This is your blade efficiency. If I call this expression as expression 1 plus 2 and this has 3, this has 4. Now we know that what is the optimum value. Already we have seen the phi optimum or phi max is equal to cos alpha 1. Already we got it. So what will be the maximum? Hence the maximum blade efficiency is equal to, the substitute for that, 2 into 2 cos alpha 1 into cos alpha 1 minus cos square alpha 1 divided by 1 plus cos square alpha 1 plus 2 into cos alpha 1 into cos alpha 1. If I substitute and simplify, what I'll be getting, actually it will be 2 cos square alpha 1, non cos square alpha will go off, actually 2 into cos square alpha 1 into 1 plus cos square alpha. Yeah, this is minus 1, so it will be 1 plus cos square alpha 1. This is your maximum blade efficiency. So they may ask this expression, show that for a Parson's turbine, the maximum blade efficiency is equal to 2 is in terms of your flow angle, that is cos square 2 times the cos square alpha 1 divided by 1 plus cos square alpha 1. Okay. This is about expressions for